this mixture of benzene and naphthalene, compared to the mixture of methanol and ethanol. One striking difference is the behavior of this particular mixture, which is what? Compared to methanol and ethanol. One striking difference is, the square, in methanol and ethanol was the linear. Remember the linear functions? Linear functions aren't going to have any square, cubes, square roots, or anything like that. Nonlinear functions will have squares, they'll have cubes, square roots, whatever. They're going to be a nonlinear dependence on x, right? And so one of the things is we aren't going to get this nice linear trend. Well, where did this equation come from? What is that equation called? The origin of this equation, how was it determined? How do you think it was determined, this particular equation? Well, let's think about science and the scientific method. Somebody just give me a refresher. What was the scientific method, the steps in the scientific method? This is not always like this, but frequently it is. The steps in the scientific method involve observation, patterns and trends, laws. Before theory comes hypothesis. Hypothesis, then theory. And so normally here's some kind of pattern, here's some kind of trend. If this pattern trend holds repeatedly and it's pretty well reproducible, then we'll call it a law. This is the law of the density of benzene and naphthalene mixtures. And where does that come from? Where does the law come from? Does it come from theory usually? Well, maybe somebody figured it out theoretically. But more often than not, a law like this comes from observations. And so being an observation-based law or observation-based equation, we call it a empirical equation. So we got an empirical equation. This just maps out the behavior of this benzene-naphthalene mixture, right? The density of it. And it's very useful to have an equation like this because we can predict the density at any percent naphthalene composition. Or if we're given the density of an unknown mixture, we can figure out what the percent naphthalene in that mixture is. And so laws can be very useful because we can do some calculations and make some predictions of that sense. But, in science, what do scientists do? What would you say scientists do? Or what do chemists do? They observe, yeah. Chemists would observe matter, right? Chemists observe matter to try to better understand it. And so here, one of the observations leads to this empirical equation, but then we start to think, why does naphthalene and benzene behave like this, whereas methanol and ethanol behave differently? What is it about naphthalene and benzene that cause it to have this kind of behavior? Because we do expect kind of a linear behavior in terms of percent naphthalene. Right? The more naphthalene, the more the density should be naphthalene-like. And so that takes us beyond, an empirical equation and beyond a law, and we start to think about, right, a hypothesis. And eventually some kind of theory, or at least integrated into existing theories. Existing theories. Because the whole, the whole goal of science is to gain, kind of a fundamental understanding of nature, and in this case, matter. We see this all the time. For example, You know, one observation led to the law of conservation of mass. You know? For example, you do a chemical reaction, and the mass before the reaction is the same as the mass after the reaction. And this happened repeatedly, you know, so much so that they call it a law, right? Otherwise, they wouldn't call it a law. And we got the law of conservation of mass. But then people started to wonder, why is mass conserved? You know, what about matter, you know, what about matter, you know, leads to the law of conservation of mass? And so when we're thinking about these types of things, you know, how does matter work? How does it function? You know, whenever you're thinking about how anything works, let's say automobile, you know, you're looking at, well, how does an automobile work? You know, well, what do? You start to observe its properties. Wow, it moves, you know, brakes, turns right, turns left, goes backwards. Those are the properties, but those properties depend on what? Those properties depend on how it's constructed, right? What it's made out of, those types of things. And so in chemistry, we're very interested in what it's made out of, you know, composition. And not just composition, but, you know, how things are built, the structure of these things. Because the composition could be steel, but, you know, the steel can be formed in a lot of different parts. And different steel parts would have different functions just based on their structure. And so we need composition structure, and then from that we can get an understanding of its properties. And so people have thought, you know, what about the composition, what about the structure of matter causes it to behave the way it behaves? That is, this conservation of mass. And so do you know what people hypothesize? People hypothesize lots of different things. You know, we have conservation of mass because... And so what was the hypothesis behind conservation of mass? You know, why did they think you know, what about matter causes it to behave in this way? I don't mean to call on specific people, but maybe Stephanie? What about matter causes it to behave in that way?
Could it be that matter is composed of atoms?
Right. Exactly. The conservation of matter led to the hypothesis that matter is composed of little tiny particles called atoms. And then that led to atomic theory, that matter is made up of atoms. And the first person to propose a meaningful atomic theory is named Dalton. He came up with Dalton's atomic theory. Dalton's atomic theory was proposed a long time ago before there were sophisticated instruments. You know, nowadays, there's no denying atoms exist. They've been observed. How do you observe atoms? You could observe atoms using a scanning tunneling electron microscope. This is an image of the surface of silicon. These are silicon atoms. Silicon atoms aren't red like this. It's just, we'll talk about it. It's just the potential. There's a very, very tiny tip, and they try to keep what they call the voltage the same. We'll talk about that a little bit later. But anyway, atoms, you can't see them with your eye, but you can use instruments to detect them and see them using instruments. Okay? And so scanning tunneling electron microscope can see the surfaces, and the surface atoms and surface molecules. X-ray crystallography, have you ever heard of X-ray crystallography or X-ray diffraction? X-ray diffraction, atoms, you don't see atoms using visible light, but if you use X-rays, you can detect atoms. And in fact, you can take an image of the atoms using X-rays, and then there's no lens that refocuses X-rays, so you have to use a computer to regenerate the image. And so the light gets scattered off the atoms, and you use a computer to refocus all that light that's scattered into an image of the atoms in the structure. It could be, a molecule or solid or whatever. It's usually a single crystal of something. And so, nowadays the proof is overwhelming that atoms exist. But what was the proof in Dalton's time? What did he have to prove that atoms exist? He had the law of conservation of mass. He had that was all his proof. How convincing of a proof is that? How many of you believe, law of conservation of mass, that means atoms. Yeah, that's great proof that atoms exist. Do you think so? No, that's why I have a tremendous amount of respect for Dalton, because, he had to go up and face all these people who had a differing point of view. They didn't, they might not have believed in atoms. Nowadays, a guy comes up to me, he gives me the book, I don't believe in atoms. I could just fall back on all this evidence. But during Dalton's time, somebody comes up and says, I don't believe in atoms, I believe in an ether. And this ether transmutates like aliens or something, from one entity to another, and Dalton came up with these atoms. These atoms are just rearranged in reaction. And so how strong of evidence is that? Are you prepared to go in front of a whole auditorium full of critics and be able to argue that atoms do indeed exist based on conservation of mass? That's tough, isn't it? But, theories should do two things. Theory should be a fundamental explanation. So the fundamental explanation of the conservation of mass is that matter consists of atoms, and they're just rearranged in these chemical reactions, right? That's a fundamental description. But not only do theories have to be a fundamental description of the experimental observations or facts, experimental facts always win over theory. If your theory does not agree with experimental fact, then your theory must be modified or abandoned, basically. Okay, so why did Dalton's theory get such widespread acceptance? Well, especially in that era, where we didn't have sophisticated instruments that could visualize atoms, manipulate single atoms. How did it get widespread acceptance? Because theories have to do two things. One, they have to give you a fundamental picture. What's happening with composition, what's happening with the structure, what's going on with matter. How's matter composed? Right? It's just not some ether, that's floating around, but it actually is made up of stuff. Right? And so that's our fundamental picture. But what else does a theory have to do? A theory must, number two, a theory must do what? Predict what? New phenomena. Good. That's good. It's you have good memory because a lot of people forget this. I talked about this on Monday, but it's already Thursday. It's easy to forget, right? 4 days ago. And this just shows, some people have like a photographic memory, others don't. I don't, I had to do this repeatedly. So hopefully by Thursday you would have seen this 4 times, at least. And then that helps you remember this type of stuff. But the theory should do 2 things. It should predict unforeseen phenomena. And so what did Dalton's theory predict? What unforeseen phenomena did Dalton's theory predict? The law of multiple proportions. And the law of multiple proportions, this is all discussed in chapter 2, by the way. But the law of multiple proportions, with that bit of evidence, then it seemed, it seems that it makes sense that matter is made up of atoms. It makes sense because if matter was made up of infinitely divisible ether, then you can combine things in any ratio or transform things into anything you want, right? And you wouldn't have the law of multiple proportions, these whole number ratios of species. And so, that was the proof that atoms exist for Dalton during Dalton's time, right? The law of conservation of mass plus an additional bonus was the law of multiple proportions, which it successfully predicted. Okay. Well, anyway. Did things like, I know a lot of people in both classes said things like the Rutherford scattering experiment. Did the Rutherford scattering experiment really predict or prove the existence of atoms? What was the Rutherford scattering experiment about? The Rutherford gold foil experiment was about the structure of the atom itself. By the time Rutherford came along, the atomic theory was pretty well established. And they were just trying to figure out inside the atom, what is the composition and the structure of things inside the atom. We know matter is made up of atoms, but what makes these atoms behave the way they behave? Like, for example, why is a gold atom different than a lead atom? Even though all gold is made up of gold atoms and all lead is made up of lead atoms, there must be something inside the atom that makes it different. And so that's later. The Rutherford, comes much later than Dalton with the atom. It could help, it could help prove, because the nuclear atom model is what he proved. Nuclear atom model versus what? Versus the plum pudding model. Electrons? Do electrons prove it? The atoms exist? Not necessarily. Does radiation and radioactivity prove it? Yeah, the certain aspects of it could, but really. But anyway, today we got lots of proof. But just because we have sophisticated instruments doesn't mean this type of challenge comes up. Because when you have proof, do you think that's a slam dunk in terms of proof? The conservation of matter is slam dunk? Oh yeah, that is good solid proof that atoms do indeed exist. Do you think so? Or do you think it's kind of shaky ground? I think it's shaky ground, and that's pretty impressive. But the funny thing is you think with all this modern technology and all this sophisticated measurement tools and other stuff, when you're doing scientific research, it's always like this. You're always the new Dalton. You just have fancier numbers and fancier equipment to work with, but you always seem like on shaky ground. I'll tell you, when I was getting my PhD, I felt, wow, I need to do another 80 years worth of experiments, and then I'll feel confident in what I'm proposing, right? But who has time to do that? You just got to take that and then interpret it the best you can. Did Dalton say, okay, let me wait until somebody invents the STEM, and then, or the X-ray diffractometer? No, he took the evidence and analyzed it the best he could. And that's it. We don't have an infinite lifetime. We don't have an infinite ability to do an infinite number of experiments. It's always like this in science. There's always uncertainty, right? And there's always error. And so, you know, the only thing you can do is you just have to deal with it the best you can. You know, and I've had lots of data that I thought was borderline, you know, garbage, and I wanted to throw it away and do the experiment over and over and over until I got data that kind of matches with what I said. You know, and some people, they take the shortcut. They take the shortcut and just fudge their data. Have you ever heard of that? You know, there's recent cases where like a paper that was submitted to the journal Nature was based on fudged data. Why did they fudge it? Well, they thought, oh, that's close enough, and they'll change a few things here and there, make it look right. But that type of stuff is, like I said, scientists are critical in nature, and if you're pursuing science, you just got to get used to the criticism. The criticism's there not to attack you. The criticism's there just to make sure you're doing good, solid work. You know, you can bet that Dalton had tons of critics, right? There's no doubt about that. But the thing is, the idea survived all that criticism, and now we see modern day atomic theory is what we use today. And so it's the same thing that's happening is, you know, it's subjected to criticism. Eventually somebody's going to find the holes. Eventually somebody found out that the data was fudged. You know, it's like the alien bacteria on Mono Lake. Did you hear about the alien bacteria on Mono Lake? You know, they said, oh, there's an arsenic-based life form rather than a phosphorus-based life form in the bacteria in Mono Lake, which is in California, Northern California. Which is kind of, like a dead lake. There's only brine shrimp that live in there. There's no fish, anything. Arsenic levels are very high. And so they found bacteria there. But it turned out that, you know, initially they said, well, this bacteria must be eating the arsenic, and it must be metabolizing it and incorporating it into its respiratory system. But it turns out that, well, it was just maybe accidental contamination, you know, because lots of people, there were lots of critics and lots of people tried to reproduce it, you know, to make sure it was right. But this is kind of the stuff that happens in science, and science is what we call a refereed science. You know, every you know, except for certain things, even you know, like some publications, you know, they don't undergo any criticism or scrutiny. But if you publish in a regular scientific journal, you have to send it out to 3 referees who try to criticize it and find any kind of weak points and ask you to repeat experiments. And so they send out a paper. They say, well, why don't you try this? Did you think about that? Did you do this? And then you have to respond to all those, you know, either by conducting the experiment or arguing against it or saying that they're wrong. And then after it's been refereed, then you finally get to submit it. Usually the process takes a long time, right? There are non-refereed journals which publish their rapid communications, but everybody knows those are non-refereed, so they can't trust the data as much, right? And so, anyway, this is part of the scientific method, and it's a self, you know, purging mechanism where, you know, a lot of the junk science is filtered out. Well, and so as a working scientist, what you do is you collect data, you come up with some kind of pattern, the pattern looks like this, and then you start wondering, why is this? We have to hypothesize something. You know, what about this naphthalene benzene mixture makes it behave in this bizarre way where we get this, you know, quadratic type behavior? You know, like this. Is this a positive or negative? Whatever. You know, what in this? And so, you know, we come up with some kind of hypothesis. You know, when we think about hypothesis, what do we want to think about? We want to think about, you know, the composition and the structure. What about the composition and structure of this mixture gives it this funny property, right? And the funny property is this equation. And so the next step here in science would be to figure out why this is. What is the theoretical basis for having a quadratic relationship here in the density Whereas we saw the linear relationship there, or vice versa. Somebody says everything should be quadratic. So why are we getting the linear relationship in methanol ethanol? You know? And so this is what scientists do a lot of. And so what we do is, well, if you knew the theory, if you know the theory, right? Theory, you can predict these things. If you know the theory, I could have predicted, oh, for that mixture, I'm going to get quadratic. For this mixture, I'm going to get linear, right? And so that's a great thing about knowing the theory. But do you think the theory is exceptionally well known? Well, what is the theory of chemistry? Is there such thing? If you think about the theory of chemistry, you go, oh, the theory of chemistry, this is going to be atomic theory because matter is made up of atoms and chemists study matter, right? But is that it? Well, what was Dalton's atomic theory? What did he state? He stated that matter is made up of these tiny particles called atoms. And the particles, he called them indestructible, but we know we can destroy them. If you destroy an atom, it no longer retains the same properties of the element that it had before, so you can't. The smallest piece of an element is the atom. But, you know, what else did he say? He said all atoms of an element are identical. Is that still true today? No, because we know of isotopes, right? Some atoms of an element are heavier than others. He said that atoms of different elements are different. Well, atoms of different elements are different, but what causes them to be different? So a hydrogen atom is different than a gold atom, and they're going to give different properties, but did Dalton's atomic theory explain or give you a fundamental description of what's going on with the atom? No. And so we have atomic theory, that is, matter is made up of atoms. Now what we have to do is we have to look at atomic composition and atomic structure to understand why atoms behave the way they do. And so this is atomic structure theory or structural theory. But getting into this, then we have to know what's important in chemistry. You know, when chemists are looking at how things work, you know, if you're looking at an automobile, you want to know, you know, what is that automobile made out of? How is it structured? How does it operate? Okay. Well, when chemists do this, we have something that's somewhat targeted in the sense that it turns out that the most important thing, and this is what the theory of chemistry is based on. The theory of chemistry is based on electrical interactions. If you want to understand chemistry, all you need to do is you need to understand electrical interactions. And so electrical interactions can be summed up like this. You know, opposite charges attract, like charges repel. The force of this electrical interaction, which I'll call F, this is given by Coulomb's law, which I'm just going to give you a simplified version here. Coulomb's law. The force of the attraction is proportional to the charge on body A, or atom B, over the distance squared. This is the distance between the center of charges. Between center of charges. This is the charge on the two bodies, A and B. And so the higher the charge, the stronger the force, and the closer they are to each other, the stronger the force. In chemistry, we don't really care about gravitational. You know, gravitational forces are weak, and so we completely ignore gravitational forces and other forces. And so pretty much the only force we're focused on are electrical forces. The theory underlying chemistry has a name to it. The theory that underlies chemistry is called quantum mechanics or quantum physics, quantum chemistry. And what quantum mechanics does is it just looks at how these electrical interactions take place in atoms, so molecules, etc. And so a lot of the physical properties can be determined by these electrical interactions. Are the electrical interactions strong? You know, if the electrical interactions are strong, then we expect high melting points, you know, harder to break things apart when the electrical interactions are strong. High boiling points. And those are physical properties. Or we expect things to be unreactive, you know, strong bonds. Strong bonds means hard to break, less likely to react. And so we're going to be looking at these. And so the first thing is we want to understand the structure of the atom. In particular, we want to look at the electrical properties of the atom as well. The physical characteristics of the atom. So let's move to a lot of this is review. But, you know, atoms, when we try to visualize an atom, we got, it looks like a little sphere here. And the first thing is atomic structure is this. Is it like a shell, like an egg shell? You know, is there a surface? This kind of looks like a hard sphere, right? But is there a hard sphere here? It's a hollow sphere. Are atoms little balls, solid balls like this, where you can just tap on the surface? Like that, when you're probing these? No. In fact, this is just to represent what we call the average diameter of the atom. The average diameter of the atom is given by, you know, how it interacts with other atoms. But really, what surrounds the nucleus is empty space. There's empty space. Well, if that's empty space, what's this wall? What's the barrier? Well, there is no wall. There is no barrier. It's just that in this empty space we find what? Electrons. And so it's empty space in which electrons can be found. What holds the electrons to this empty space? Because if I have more than one electron, they want to repel each other. You know, and they'll scatter in every direction, right? And so what holds the electrons in this empty space? The nucleus, because inside the nucleus we have protons. And the protons, you guys are familiar with the symbols, right? P plus for proton, E minus for electron. The nucleus with the protons is going to hold the electrons so they don't go too far away. And that's called electrical attraction. The electrical attraction, what holds the electrons inside an atom? Well, the protons, because there's a positive and negative attraction. Well, the same thing here, you know, and so we have a lot of negative charge here. And so in the STEM, they have a probe, and the probe measures what we call the electrical potential, or the charge, you know, density. And this probe tries to keep the electrical potential, or the voltage, or the charge equal. And so when the electrons get too dense, it goes out. And when the electrons get less dense, it goes in. And so we can see the electrons are kind of contained in this. Not exactly contained, because electrons can be found outside this as well. And so what we have here is we have something called the average diameter or the average radius if you go from the center out. What else do you know about atomic structure? The neutrons. The neutrons are found in the nucleus. All right, let's talk about the electrons. We need to do a little bit of a historical review. And who determined, or who kind of discovered the electrons? Let me rephrase that. Not electricity, but electrons that are part of atoms. Who discovered that? Not Dalton. You know, Dalton was just atomic theory, atoms. It's hard to remember, isn't it? Because Chem 4 was so long ago. You know, my friend, I have a pre-med friend, graduated in biology, and he asked me, this is at UCLA, he asked me to help him review chem. You know, he took general chem years prior. And so I said, sure, I'll help you review chem. And so then we started reviewing, and I started asking him some questions. You know, what do you remember? Well, basically, he remembered nothing of general chem. And we would have to start from almost complete scratch because he completely forgot it all. And what he did was he decided there's no way he was prepared for the MCAT. And so not only did he take 1 year off, he ended up taking 5 years off reviewing and refreshing his memory to get prepared for the MCAT. You know? And so, you know, my advice to people who are preparing to take MCATs or something like that, you know, MCAT's a lot of general chem, a lot of this stuff on there, is to, you know, you got your notes and you review them periodically. Maybe not every day, but you review them once a month or something to at least, if your memory fades like mine, you know, you can remember a little bit. You know, this guy didn't remember anything. You know, and a lot of it is just recall. You know, on a lot of tests, what I found when I was a student at UCLA is I didn't have to think of anything genius. I didn't have to think of anything new. All I had to do was be able to recall information. So if I had a photographic memory, I figured I could get a guaranteed A in the class because 90% of the test was, do you remember what this professor said, you know, 3 weeks ago? If I did, then just write it down. Don't have to do anything on top of it. And so it's just kind of regurgitation of information, which isn't anything, you know, it's like what they call that first order, first level thinking or whatever, or learning or understanding. But anyway, you know, what I found was, oh, no, I didn't remember. I didn't remember what the professor said 3 days ago, you know? It's hard to remember that type of stuff. And so this is the reason why I started reviewing every day, you know, especially for the final. I'll tell you, before I started reviewing every day, did I talk about reading my notes every day? Yeah. Before I started doing that, my stress level before the final was like this, you know, totally stressed out, too much stuff, overwhelmed. But after that, you know, it was way easier. The stress level goes way down, a lot easier to prepare when you can recall things a lot easier, you know. You're not learning it new again, you know, right before the final. And so, you know, if a lot of this stuff is not review or you've lost it, then maybe review your Chem 4 notes. You know, that would be helpful for this class as well because I'm skipping some of the review stuff, just expecting you to know it. At UCLA, they pretty much skip the first 4 chapters saying, oh, that's all review. We'll start with chapter 5. You know? Doesn't mean they'll test you on it. They might. You got to be prepared. But anyway, let's review the electron. It was J.J. Thomson. I don't really expect you to remember dates or names or anything like that, but there are certain people. Dalton, yes, I want you to know who Dalton is, right? You know, you have to have respect for somebody like Dalton to come up with atoms from conservation of mass. J.G. Thomson. J.G. Thomson's good because he came up with the CRT. Do you remember what the CRT stands for? Cathode ray tube. And what did he do with the cathode ray tube? Let's talk. Might as well take a look at the cathode ray tube. We have one, but it got cracked. Can't demo it. For the cathode ray tube, we should know a little bit about electrical interactions here. Like charges repel. Neutral, neutral. This is just gravitational. This is overcoming some gravitational. Here, unlike charges attract. Charged species can interact with magnetic fields here. Positive charge might be deflected like this. Negative charge species would be deflected the opposite way. Charged species can also interact with electric fields. And so here's the cathode ray tube here. A cathode ray, you know, in this tube we have what are called electrodes. And then you hook up something called a voltage supply or a power supply to this. What a power supply does is it sucks electrons from one electrode and gives it to another electrode. And so in this case, in this power supply, the power supply is pulling electrons off this. Usually it's a piece of metal. And so you pull electrons off this, and you force the electrons over here. This part is called the cathode, and hence the name cathode ray tube, because the electrons originate at the cathode here. And the electrons, they're negatively charged species. And so this is a negative electrode, this is a positive electrode. So the electrons are going to be accelerated towards the positive electrode. There's a hole in this positive electrode, so electrons can actually shoot past the positive electrode based on momentum and can continue. And so here, they put an electric field here, so we can see that these cathode rays are negatively charged because they're attracted to a positive plate. This electric field is generated in exactly the same way, it just isn't as strong. This is very strong. In a cathode ray tube like this, you need on the order of 5,000 volts of potential to generate cathode rays. And that's 5,000 volts because in a cathode ray tube like this, what they do is they create a vacuum. That is, they hook up a vacuum pump and suck out most of the gas inside here. And so it's easier to break down. If this were air at 1 atmosphere, you'd need tens of thousands of volts to generate a little lightning bolt like this. And this is like little lightning, mini lightning here. But anyway, we can generate an electric field like this. We suck electrons from this plate and put excess electrons on this plate. You know, metals, electrons flow freely, right? We generate electricity. And so we see that the cathode rays are negatively charged. They also interact with magnetic fields. They're deflected, as you would expect for particles that have negative charge. And you can cancel out the effects. So if we put an electric field and an opposing magnetic field, then nothing happens. They oppose each other. One tries to deflect one way, the other tries to deflect the other way, and nothing happens. Here. And so what are these cathode rays? Well, the main conclusion of the J.G. Thomson CRT experiment, the cathode ray tube experiment, is that electrons are a fundamental part of all matter. These cathode rays are made up of beams of electrons. And the way they determined that was they changed the cathode. You could make the cathode out of other metals. So for example, if this was made out of iron, they changed it to aluminum. When you change it to aluminum, they got the same cathode rays originating. And then they change it to whatever. Brass, which is a mixture, a homogeneous mixture or heterogeneous, depending on how microscopically you look at it. But you change the material of the cathode ray and we always generate the same cathode rays. In other words, you change the material of the electrodes here. And so it appears that whatever makes up cathode rays is present in all matter, and whatever that is, to make a long story short, it's the electron. And so this is kind of the discovery of the electron. J.J. Thomson was credited with that. Also with the cathode ray tube, you know, that led to the discovery of the electron, but it also led to something else. You know, electrons, I guess lightning, you know, precedes this, and electricity might have preceded this. Well, obviously electricity's got to have preceded this, because in order to make that cathode ray tube, you needed electricity. And so this is discovery of electrons as a part of matter, as a part of matter. Matter is made up of atoms, and so it is a part of atoms. Okay, the other thing is this, the angle of deflection. The angle of deflection here depends on how much these particles weigh. If these particles are very light, then they're deflected easily. If the particles are heavy and massive, then there's a lot more inertia, and they aren't deflected as easily. And so based on the angle of deflection, we could get the mass to charge ratio. From the angle of deflection. And so generating electric fields can be more work than just getting a bar magnet. So you get a bar magnet or some kind of magnet here, and then just measure the angle of deflection here. And so by measuring from the angle of deflection in magnetic fields, or in a magnetic field. Okay, that's the electron. How was the proton discovered? The proton was discovered using these types of techniques, but it's also talked about in Petrucci, but you don't have to know. I'm not going to ask you how the proton was discovered. How was the neutron discovered? No, I'm not going to ask you that either. So you could say, I don't know, and that's fine. I'm not going to deduct any points for that. But somebody discovered it, right? They probably want to be remembered as well, you know, as the discoverer of the proton. But we aren't. We're going to focus on the electron. The next thing about the electron is the Millikan oil drop experiment. What did the Millikan oil drop experiment do? Exactly. Figured out the charge on an electron. And so let's take a look at the apparatus here. Here it is. What we have is a fine mist of oil drops. The fine mist of oil drops are going to be subject to gravitational forces and fall. And so they're just going to fall at this rate, whatever that rate is. We expose these oil drops to an electric field. This is the symbol for a battery. And so what they do is with this battery, they're going to pull electrons off this plate and push electrons onto this plate, making this plate positive, this plate negative. Oil drops are neutral. And so are neutral oil drops attracted to either charge? No, they're unattracted. And so these are just going to fall according to the force of gravity. Okay, then this X means we're going to subject this to ionizing radiation, like X-rays. What Millikan had was he had a radioactive source. Now, nuclear reactions don't follow the same rules as chemical reactions. Chemical reactions are dictated by electrical forces. Do you know what nuclear reactions are dictated by? Not electrical forces. Nuclear chemists don't really care much about electrical forces. Nuclear chemists care about nuclear forces. Why? Because nuclear forces are much, much stronger than electrical forces. Chemists don't care about gravitational forces because gravitational forces are much, much weaker than electrical forces. Nuclear chemists don't care about electrical forces because electrical forces are much, much weaker than nuclear forces in which they deal with. And so what they had is they had some kind of radioactive atom, and that radioactive atom was unstable. In fact, the radioactive atoms, they have unstable nuclei. The nucleus is unstable. And the nucleus breaks apart. When that happens, it emits radiation. And in this case, it emits X-rays. And so as X-rays are emitted, X-rays can hit air molecules. When X-rays hit air molecules, it can knock electrons off, creating ions. And what tends to happen is if you have an ionized nitrogen molecule, the electron wants to reattach and make it a neutral nitrogen molecule, or an ionized oxygen molecule. But once in a while, the electron won't reattach to the ion. Once in a while, the electron will attach to the oil droplet, making the oil droplets negatively charged. Now, if the oil droplets become negatively charged, then there's two competing forces. Force 1 is the gravitational, force 2 is the electrical, and the electrical is trying to pull the droplet up, the gravitational is trying to pull it down. And so, based on how many electrons they attach to the drop, because if the drop's pretty massive, then you got to attach quite a few electrons to that to get the oil droplet to stop or actually be pulled in the reverse direction. And so based on how the oil droplets fell or didn't fall, he was able to determine the charge on an electron. And so J.G. Thomson had this. Millikan determined the charge of an electron. If we know the charge of an electron, and we know the mass to charge ratio, then we can use dimensional analysis, cancel out the charge, and determine the mass. And so the mass of an electron was determined by calculation. The calculation has gotten much better. The original calculation for the mass of electrons is quite a bit off because of the accuracy and the precision of the earlier instruments. But now it's much more accurate, much more precise. So we have a good one. Value for that. And so we know this. We know the charge of an electron. Well, we know the mass of an electron. What don't we know? We don't know the size of an electron. So if this is a helium atom, are electrons this big, like this blue ball here? Much smaller? Much bigger? How big is an electron? You'd expect an electron to be tiny because it's got to fit in the atom. And so how big is an electron? Has somebody measured the size? Is an electron a round ball? And somebody's measured the diameter? What is the diameter of an electron? That is a very tough question. Why is that such a tough question? Because this thing, this quantum mechanics stuff, describes electron as nothing you've ever seen before, right? It's neither a particle, and so it's not like a ball or a sphere, and it's neither a wave. It's kind of a wave and a particle or something like that. Or if you watch, the Hadron Collider, have you heard of that thing in Switzerland? If you watch that, then they'll say, how big is an electron? An electron's zero. It has no size. It's nothing, right? And so what is it? Well, it's just this wave that passes through this Higgs field or whatever they call it and picks up mass, right? It's another way of thinking. And so electron is, if you're looking for the diameter of an electron, you aren't going to find it. There's no book that's out there that's going to tell you the diameter of an electron because nobody knows exactly what an electron looks like, right? And it has very weird behavior. That's discussed later. All right, so let's take a break here and then we'll continue with the structure of the atom.